series. Okay, and here let us consider the sequence. Let it be some un. Okay, already you know this one. The sequence has the first term, second term, third term. Okay, so like that every sequence has some particular number of terms. Okay, now here I am writing that number of terms in the form of some u1 plus u2 plus u3 plus and so on plus un plus and so on. Okay, so if we represent the given sequence in this particular form, then it will be called as a series. Okay, so usually we are going to use the notation as summation un, or in particularly summation n is equals to 1 to infinity un. And moreover, here in this expression the term un is called as the nth term of the series. Okay, next, generally these series are categorized into two types, finite series and infinite series. So here let us consider this representation u1 plus u2 plus and so on un. Okay, so here this expression consisting of some finite number of terms or some countable number of terms, then this type of expression or this type of series is called as a finite series. Okay, now let us consider the another representation u1 plus u2 plus and so on plus un plus and so on. Okay, so this expression or this series consisting of some infinite number of terms or uncountable number of terms, then it will be called as a infinite series. And already we discussed the term un is called as the nth term of the series. Next, the nth partial sum of the given series. Next topic, nth partial sum of the series. Okay, so here let us consider summation n is equal to 1 to infinity is an infinite series. Okay, now here I am taking some u1 plus u2 plus and so on plus un, means here we are taking some n number of terms, and I am denoting that one with some sn. Okay, so this type of representation is called as a nth partial sum of the series. Means in this expression we have some n number of terms, so that's why we are saying it is called as a nth partial sum of the series. Okay, so here I am giving some examples. So s1 is equals to some u1. Okay, means it consisting of only one term, so it is called as a first partial sum of the series. Next, similarly s2 is equal to u1 plus u2. It consisting of only two terms, so is called as the second partial sum of the series. So similarly s3 is equal to u1 plus u2 plus u3 is called as the third partial sum of the series. So next we are going to discuss about the nature of the series. Okay, so here in this one we are going to discuss about the convergence, divergence and oscillatory. So first we are going to discuss about the convergence of a series, when the given series is said to be convergent. Okay, so first of all, summation n is equal to 1 to infinity un is a given series. Okay, now here next we will consider the nth partial sum. We are taking the nth partial sum of the given series. If we calculate the limit for that nth partial sum, that limit value is finite, then it will be called as the convergence of a series. That means limit n tends to infinity, Sn is equals to finite. Okay, so this is about the convergence of a series. So next, divergence of a series, when the series is said to be divergent. So first of all, let us consider the given series summation n is equals to 1 to infinity un. Okay, now here I am taking the nth partial sum. Let it be some Sn. Okay, so for that nth partial sum, if we apply the limit, if you will get the value as some infinite, then it will be called as the divergence of a series. That means limit n tends to infinity, Sn is equals to infinity, then it will be called as the divergence of a series. So next, oscillatory of a series. Okay, now summation n is equals to 1 to infinity un is said to be the oscillatory series if the limit of this nth partial sum is not unique. means we are getting more than one limit. Okay, so for the nth partial sum, if you find out the limit, if you will get more than one limit value, then it will be called as a oscillatory series. Okay, now here I specified one example, summation n is equal to 1 to infinity k. Okay, so first we will consider the nth partial sum. So Sn is equal to k plus and so on up to like this. We have to write n number of times. Why? Because we are saying nth partial sum. So which is equals to nk. After that we will consider limit n tends to infinity Sn. So which is equal to limit n tends to infinity nk. Okay, so here k is a constant. I am writing before the limit. So k into limit n tends to infinity n. So which is equals to k into infinity. Why? Because as n tends to infinity, that limit value will becomes infinity. So we got limit n tends to infinity Sn is equals to infinite. Therefore the given series is a divergent series. Okay, so next see the second example, 1 plus 2 plus 3 and so on. Okay, so what is the series representation? Summation n is equal to 1 to infinity an. So first of all we have to consider the nth partial sum. So Sn is equal to 1 plus 2 plus 3 plus and so on, like this n terms. So the sum of the first n terms is n into n plus 1 by 2. Now let us consider limit n tends to infinity Sn, which is equals to limit n tends to infinity n into n plus 1 by 2. As n tends to infinity, this total value is tending to infinity. Therefore the given series is divergent. So like this we have to check whether the given series is divergent or convergent or it is a oscillatory sequence. Okay, so next we are going to discuss about the geometric series. Okay, now here the series having this particular representation. What is this one? A plus AR square plus and so on, AR power n minus 1 plus and so on. Okay, means the first term is multiplied with R, then you will get the second term. If the second term is multiplied with R, then you will get the third term. Like this it will be going on. Okay, so summation representation is summation n is equal to 1 to infinity a into R power n minus 1. So this type of representation is called as a geometric series. Okay, so in this geometric series the first term is A. So A is the first term of the series and common ratio will be given by second term divided by first term or third term divided by second term or fourth term divided by third term. Like this it will be continued. So the common ratio will be denoted by R. Okay, so the ratio between the successive two terms should be same. Okay, now this type of geometric series is convergent if modulus of R is less than 1. Means if R value lies between minus 1 and 1, then the given geometric series is convergent. If R greater than or equals to 1, then the given geometric series is divergent. If R value is less than or equals to minus 1, then it will be called as the oscillatory sequence. Okay, so this is about the geometric series and the nature of the geometric series, whether it is convergent or divergent. Okay, next. So here summation n is equal to 1 to infinity a into R power n minus 1, which is a geometric series, and always it is converges to a by 1 minus R. Okay, so a by 1 minus R. This is applicable only if R is less than 1. If R is greater than 1, then you will consider a by R minus 1. Okay, so here we have some properties regarding this series. Okay, so if we add some terms or if we delete some terms from the actual series, even though the nature of the series does not change. Okay, next, the second point, if summation un converges to A and the summation Vn means the series is converges to B, then summation un plus Vn converges to A plus B. Okay, next, if summation un converges to A and C is a constant, it's a real value, then summation C into un is also converges to CA. Okay, next, necessary condition for the convergence of a series. So let us see the theorem statement, if the series summation un is convergent, then limit n tends to infinity un is equals to 0. So what we have to prove here? The given series summation un is convergent, then what we have to prove? Limit n tends to infinity un is equals to 0. Okay, so let us see the proof here. What is the given series summation un, and which type of series is this? It is a convergent series. Okay, so means the limit of the nth partial sum, the limit of the nth partial sum is equal to some finite value. Okay, let it be some limit n tends to infinity. Here we are denoting that nth partial sum with some Sn which is equals to finite. Let it be some L. Okay, so similarly here I am taking the n minus 1th partial sum of the series. Okay, so here I am denoting that n minus 1th partial sum as s suffix n minus 1. Okay, that is u1 plus u2 plus and so on un minus 1. Okay, so if this nth partial sum is finite, okay, so here the n minus 1th partial sum is finite. Okay, now we have to prove limit n tends to infinity un is equals to 0. So for that purpose here I will consider un, and here I am expressing this un as Sn minus 1. Here Sn denotes the nth partial sum and Sn minus 1 denotes the n minus 1th partial sum. Okay, so now consider limit n tends to infinity un, which is equal to limit n tends to infinity Sn minus 1. Okay, so next we are applying the limit for each and every term separately. So limit n tends to infinity Sn minus limit n tends to infinity Sn minus 1. So already you know that one, limit n tends to infinity Sn is equals to L, and limit n tends to infinity Sn minus 1 is also L. So L minus L you will get 0. Therefore if the series is convergent, then the limit n tends to infinity un is equals to 0. Okay, but converse of this statement is not true, need not be true. That means if limit n tends to infinity un is equals to 0, then the series summation un need not be convergent. Means it may be convergent or may not be convergent, means it may be divergent. Okay, but we have the another condition also. If limit n tends to infinity un is not equals to 0, then compulsory the series summation un will becomes the divergent series. Okay, next in the next topics we are going to check whether the given series is convergent or divergent. So for that purpose here we have the different test. Okay, so here first I am going to explain about the limit comparison test. If summation un and summation vn are two series of positive terms, okay, and here if the limit n tends to infinity un by vn is equals to some L and it clearly not equals to 0, then the nature of un and vn, the series un and vn will be same. Means both summation un and vn are converges, or summation un and summation vn are both can be diverges. Okay, so this is about the limit comparison test, and moreover these tests are applicable only the series of positive terms. Okay, so first we are going to discuss about only the series of positive terms. Series of positive terms means each and every term of the series is positive, means it is greater than 0. Okay, next auxiliary series, or it will be called as a P series also. So an auxiliary series, what is the representation of the auxiliary series? Summation n is equals to 1 to infinity 1 by n power p, nothing but 1 by 1 power p plus 1 by 2 power p plus and so on 1 by n power p plus and so on. Okay, so this auxiliary series is convergent if p greater than 1, it will be divergent if p less than or equals to 1. Okay, so next here I am giving one example for the limit comparison test. So test for the convergence summation square root of n square plus 1 minus square root of n square minus 1. Okay, so this is a given series. So here what is the nth term? Un is equal to square root of n square plus 1 minus square root of n square minus 1. Okay, so here Un is equals to, I am rewriting the term as square root of n square plus 1 minus square root of n square minus 1 into, I am dividing and multiplying with square root of n square plus 1 plus square root of n square minus 1. Okay, so here the numerator is in the form of a minus b into a plus b, so you will get a square minus b square. Okay, so after the simplification you will get 2 by square root of n square plus 1 plus square root of n square minus 1. Okay, now in the denominator we are taking n square is a common. Okay, then it will be 2 by n into square root of 1 plus 1 by n square plus square root of 1 minus 1 by n square. Okay, so in the limit comparison test we need two series. Okay, so summation un is a given original series. Now here I am creating one duplicate series or dummy series for our convenience. Okay, so here I am taking that series as Vn is equal to 1 by n. Okay, so from this un only you have to create the Vn. So un is what? Finally simplification 2 by n into square root of 1 plus 1 by n square plus square root of 1 minus 1 by n square. Okay, now here according to my convenience to get the auxiliary series form, here I am taking Vn as 1 by n. Okay, so after that in the limit comparison test you have to consider limit n tends to infinity un by Vn, which is equals to limit n tends to infinity. So let us calculate un by Vn. What you will get here, 2 by square root of 1 plus 1 by n square plus square root of 1 minus 1 by n square. So if you substitute the limit as n tends to infinity, you will get the value as 1. So here clearly limit n tends to infinity un by Vn is equals to some L, that is 1, which is not equals to 0. Okay, so what is the limit comparison test, or what is the auxiliary series definition? So here if p greater than 1, then it will be convergent. If p less than or equals to 1, divergent. That is the auxiliary series definition. In the limit comparison test, limit n tends to infinity un by Vn is equals to L, which is not equals to 0. Then un and Vn have the same nature. So here we got 1 which is not equals to 0. Therefore by using the comparison test we can give the conclusion as summation un and summation Vn both are behaving in the same way. Okay, and here from the auxiliary series or by the p series, summation Vn, summation 1 by n means here p is equals to 1. Okay, so you know that one, if p greater than 1 it will be convergent, p less than or equals to 1 it is divergent. But in this example we have p is equals to 1, therefore summation Vn, that is summation 1 by n, is divergent. Okay, so here clearly summation Vn is divergent, then summation un also divergent. Therefore the given series is divergent. Okay, so this is about the limit comparison test. In the next class we are going to discuss about the ratio test, D'Alembert's ratio test. Thank you.